All right, class, can you see me? Can you hear me? Um, okay, I think we're getting good results. I'm in a different location all the time. I'm somewhere else. I'm in the computer science building. I keep changing the rooms. So, we got a lot to do today. Uh, where is it? Okay. Hi, I'm just saying hi. That's the camera in the lid of the laptop. It's not very good resolution, but it works. All right, we have a lot to do. Let's go back to the other camera. And uh, yes, okay, so I'll just announce it, and it's up to you what you want to do with the information. It's today, the 22nd, is the job fair. Except my marker is terrible. Job fair. In Titan Student Union. Now, the odd thing is it overlaps class time right here. It runs from 3 to 6 p.m. So, well, finish class at 4 and then go over there and see what they're doing. Um, it's never too late to learn how the process works. Those who have prepared well will succeed. It's not something job searching is not something you suddenly decide in April of your graduation semester. I think I'll search for a job now. It's an ongoing process that you refine month by month or semester by semester. Okay, so that's the announcement. TSU at 3 to 6 o'clock. Okay, you should talk to the recruiters. Just ask what kind of jobs are they hiring for. You might decide how to tailor your future elective classes if you had information like that. Going on, my goal last week and still today is that we catch up with the Monday, Wednesday class, and then we're almost there. By the way, it's working. And after we're so-called caught up, then I want to go to the schedule of 1 hour lecture followed by 1 hour of open lab. Open lab, that's where questions and answers, answer programming questions, answer questions about error messages, how to debug programs, how to fix known error messages. That's the open lab. And hopefully we can save a few minutes at the end of today for this one. But I want it to be a regular feature. I'll stay with you the full 2 hours. It's up to you how much good you want to get out of it. Okay. Let's I should keep the chat in front of me and so I can see if there any questions come up. Let me fix this. All right. Last week we left off with binary integers. And we saw that in a register, let's use 16 bits. 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1. Okay. Then if you're not told in advance, we go to the default assumption that the bits are numbered 0 here, 1 here, 2 here, 3, 4, and this would be bit number 15 back here. Is that the center of the page? Just barely. Okay. In a lot of assembly and architecture textbooks, this will be written in there. I've never seen one that deviated. You number the bits, number 0 here, 1, 2, 3, out this way. I just don't have room to draw 64 of these bits, but the same numbering scheme would progress from 0 to 63, in fact. And the reason for that is that that bit on where my finger is, that has the value of 2 to the 0. And the one next to it has value 2 to the 1. The one next to that is 2 to the 2. And the one next to that is 2 to the 3. And it keeps going, 2 to the 4th. And this is 2 to the 15th. That last bit on the, actually, I didn't tell you that correctly. That's actually the sign. In a sense, it doesn't have a value. So the one next to it has the value of 2 to the 14. And that 0, where I'm pointing now, means that it's a positive integer that follows. Okay. That's a, let me cross off 2 to the 15. That stands for sign. Okay, so the numbering scheme goes like that, and that plays a role in what we're going to do in a few minutes. Okay, so we need to know conversions, meaning we want to be able to convert from a decimal integer to a binary integer of equivalent value to a hex integer, and then reverse this and go back the other way. Well, let me see. One of these is easy. Okay, I'll show you the easy one first. I think we did it last week. If you start with a binary integer, do I have one up above there? Yeah, let's use the one that's on the previous sheet of paper, and it says sign 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1. Okay, this is tedious, but we'll do it at least once. That represents 2 to the 0. That represents 2 to the 1st. And I'm going to skip the zeros because they don't play a role, but this represents 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. I won't be able to squeeze it all in. 2 to the 6th, 2 to the 7th. Okay, and then that would be 2 to the 8. So that one is a 2 to the 9, and that'd be 2 to the 10 to the 11th. And that one is 2 to the 12. 2 to the 12, 13, 14, 15. We start counting from 0. So the number up above is equal to the 2 to the 12 plus 2 to the 11 plus 2 to the 9 plus 2 to the 7 plus 2 to 6 plus 2 5 plus 2 4 plus 2 1 plus 2 2 2 0, like such. I'm not going to figure that out. You need to use a calculator at this point. What if you have a smaller? Let's do a 1 byte number. 0 1 0 1 1 1 1 0. Okay. Counting 0 1 2 3 4 5 6. That number is 2 to the 6 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 1. And I dropped out the zeros. And whatever that adds up to be, 64 plus 16 plus 8 plus 4 plus 1, 80, 88, 92, looks like 93. That's this number back here. Okay, That's the direction of from binary to integer, decimal integer. Here's a decimal integer. We started with a binary integer here. You know, in test time, to set the foundation for the discussion, it's up to usually me to specify how many bits we're talking about. Is this I'll show you why it makes a difference. In 8 bits, this number 10111011, that's the same number. 2 zeros and a 1. Okay. In 8 bits, that's a negative number. But in 16 bits, one, two, three, four, 1, 2, 3, 4, 1, 0, 1, 1, 1, 0, 0, 1. That's a positive number. Okay, so it's up to me on test time. I'll specify, okay, this is a conversion from binary to the decimal, and the binary is given to you in 16 bits or 8 bits or 32 or whatever it happens to be. I rarely use odd numbers like 12 because no computer ever used a register of 12 bits. So we're always going to talk about this many, 8, 16, 32, and 64 bits. And remember, this is called byte. This is called word. It's called double. If you want, it should be double word. And this is quad. Or completely, you say quad word. Okay, let's go the other direction. Let me watch the questions. Isn't 2 raised to the 1 a 2? Yes, it is. Didn't I do that? Oh, gosh. Hey, Greg, thanks. For those of you recording it, let's get the correction here. 2 raised to 2 raised to the 1 is 2. Yes, yes, absolutely right. Okay, thanks. Anytime you see me make math errors, feel free to jump in. I prefer accuracy rather than fame. All right, now we're going to go the other direction. Let's suppose we start with a decimal integer. Okay, and it's kind of not real simple. Let's take a big one. 1141. Okay, you ready? There's an algorithm you should know about, but then we'll find a shortcut when it's all over. The official algorithm is divide by 2 repeatedly. Let's start the whole thing. 1141 goes 5, 10, 1, 4, 7, 14. Bring down a 1, and 1's left over. Oh, yeah, I didn't do something right. Okay, you bring down a 1, you try to divide 2 into 1, it goes 0 times, and 1 is left over. I think that's the proper way to do 3rd grade math. Okay, 2 into 570. Okay, here we go. 25, 26, 27, 28. I think it's 28. 56, 1, 0, 5, 10, 0 left over. Okay, 2 into 285 goes 14 times, 28, 0, 5, 2 times, 4, 1 left over. Next, you have to keep going down until we run out of data. This is why this is the long algorithm. 2 into 142 goes 71. I can actually do that one. Remainder 0. 2 into 71 goes 35, 70, 1 left over. 2 into 35 goes 17, 34, 1, 2 into 17 goes 8, 16, 1, 2 into 8 goes 4 times, 2 into 4 goes 2 times, 2 into 2 goes once. Okay, 2 into 1, we're getting close to the end. It goes 0 times. Put a 0, 1 left over. 2 into 0, this is kind of dumb now. 0, 0 times 2, you put a 0 here and you get a remainder of 0. If you kept the pattern going, you're just going to have a bunch of zeros. 0 goes 0 times 0. So we stop, as it was what I'm saying. Is there's no point in what I'm doing right now. 0 times 2, put a 0 here, subtract, get a remainder here. Okay, apart from, it had some meaning up to here. But after this, it's kind of meaningless. So what is the answer to our question? What is 1141? The answer is given in the remainders if you read them backwards. So where my pencil is pointing, that's a 1. Then it's 0, 0, 0. And then it's 1, 1, 1. And then a 0. Then we go to the previous page, and it's a 1, 0, 1. Okay, I think I got them backwards correctly. 1, 3 zeros. Yeah, I think so. Anybody see a mistake? That's it. That is the binary representation of this, except I'm supposed to specify this is an answer for 1 byte, 2 bytes, 4 bytes, or 8 bytes. Let's say we want an answer for 2 bytes. Does everyone remember what's another name for 2 bytes?
Was that a word?
Correct. That's right. We want a 1-word answer for this. 1 word only. Okay. So I'm going to add leading zeros. Notice that's where these leading zeros came from. 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Got kind of crowded, but I'll write it again. 1, 2, 3, 4. Yeah, no, let me be more careful. There's 4, there's 4, there's 4, and there's 4. Okay. And then 0. We get 120 zeros in here. That's a 1. And then 0, 1, 0, 1. Okay, after careful counting, I come up with the right answer. So here is the 1-word answer for the number 1142. 1141. Okay. Now, once you have a number in binary, it's not hard math. It's just thinking to convert it to hex. So here we go for the next step. 4 bits of 0 is just hex number 0. That number is equal to a 4, both in decimal and in hex. That number is equal to 7, both in decimal and hex. And that number is a 5. So the second answer is properly written as 0x0475 equals 1141 base 10 equals this one in the box. Okay. Everyone's got it. That's even though they look like decimal digits, they rightly should be considered as hex digits. A hex digit contains 4 bits. Every hex digit contains 4 bits. That will always be the case. Okay, so the long algorithm to convert a decimal integer to binary is called successive division by 2. Successive division by 2. Okay, and you saw me do it, and then you get a bunch of remainders, and you read the remainders back to yourself in reverse order. Reverse order of the remainders. And since you're dividing by 2, the remainders are always 0 and 1. It just works out nicely that way. Okay, so that works on any integer up to, there is no limit, 5,680,372. That number will be convertible to binary if you divide by 2 enough times. Okay, so now we come to the short algorithm for small integers. It works effectively on small integers like under 2,000, or that doesn't sound small, but relative to 5 billion, that is small. Okay, the short algorithm says you start with a number like 1897. And then you count in your head by powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. 2048 is too big. 1024 is just right. And subtract 3, 7, 8. Okay, so I put down one value of 1024, but I should write it in exponential notation. That's this one. Okay, and we repeat the process. Counting powers of 2, you go from 128, 256, 512, 1024 is too big, so 512 is just right. 1, 6, 3. So over here we put +1 of 2 to the 9. Repeat the process again. 128, 256, 256 just right, 256. And we get 501. So +1, 2 to the 8. Okay, in your head, you know that 64 is the highest power of 2, less than that one, 64. So you subtract, you get 41. So you say plus 1 of 2 to the 6. 2 to the 5 is 32. We're getting ones all the way. 32. So +1, 2 to the 5. And we're left with 9. 2 to the 4 is 16. That doesn't do us any good. +0 of those, 2 to the 4. 2 to the 3 is an 8. That helps. So we say +1, 2 to the 3. 2 to the 2 is 2. Doesn't do us any good. 0 it out. 2 to the 1 doesn't do us any good. 0 it out. 2 to the 0 is a 1. That helps. Plus sign, 1, 2 to the 0, and you subtract off 1, and now we're down to nothing left. We're done. So you read your answer by looking at the coefficients in front. 1, 1, 1, 1, 1. 5 ones in a row. then a 0, a single 1, 2 zeros, and a single 1. Now, my responsibility is supposed to tell you how many bits that are supposed to be in the answer. If you left it the way it looks, it's a negative number. See the 1 over here? That doesn't fit right because our number is this one. Okay, so I'm supposed to tell you in a test question, this is for a 16-bit one-word answer. All right, so let's fix it for a test answer. 1, 2, 3, 4. And I got 4 zeros and 2 zeros. 0, 0, 0, 0, 0, 0, 1, 1. That's to here. And then 1, 1, 1, 0. And then 1, 0, 0, 1. Okay, if the start of the program said our registers contain exactly one word, then you'd be thinking in those terms, and then you got that intermediate answer, and then you get the hex answer by converting the groups of 4 to be hex digits. So 0x, four zeros is 1 hex 0. That's a 3. The next one is numerically it's 14, but that's an E. And the last one is a 9. Okay. Where did 2 to the 7 go? Gee, man. Okay, 2. Okay, we got a real problem here. Am I missing a 0? Okay. Okay, I gotta fix this. Okay. That's 2 to the 10. That's 2 to the 9. That's 2 to the 8. Ah, 2 to the 7 is 127. 128. What am I saying? It's the answer is, oh, gee. You know what? Don't be upset. I want to scratch. The 2 to the 7 has a 0 in front of it, but I did it really sloppy. Wow. Okay, I'll speed it up. 1897 minus 1024. 378. 1, 2 to the 10. Okay, 2 to the 9 is 512. 163. Okay, that's good right here. 2 to the 12, 2 to the 9. 2 to the 9. Okay. 2 to the 8 is that's 256. Minus 256 is 501. Yeah, that's what I had before. So this is 2 to the 8. Okay, plus 1, 258. 1, 2 to the 8. Okay, 2 to the 7. Do I have that? 2 to 7 is 128, but 128 is too big here, so we can't use it. We go to the next one. 2 to the 6. That's 64. 1, 4. That's 2 to the 6. Okay, well, next number lower is 32. That's 2 to the 5. And there's a 9 left over. 2 to the 5. Okay, next number lower is 16. We can't use it. 2 to the 4. Next below that is an 8. We can use it. 2 to the 3. The next number below that is 2 to the 2. We can't use it. The next number below that is 2 to the 1. We can't use it. The next number below that is 2 to the 0. We can use it. The 0 says we're done. Now, answer is 1. I'm reading across up here. 1, 1, 1, 0, 1, 1, 0, 1, 0. And then 0, 1. There's 4, 6, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bits in the raw answer, but this is not good for a computer register. That's 11 bits. It looks like it's a negative number, which is all wrong. It's not a negative number. So in a test question, I have to specify one word register. So I had 11 here. We got to get 16. I need 5 zeros. 1, 2, 3, 4. Did I make any mistakes? Okay. And now we'll use red. This is a 0. This is a 7. This is a 6. It's poor red, but and this is a 9. Okay. Okay, in hex, it should be written with its proper prefix. 0769. Okay, you're all comfortable with integers. We're going to leave the subject and go on to the next part. All right, so I don't see any questions. I'm taking this from chapter 3 of your ebook. 3. And the author is very concise. He just gives a short description and says, that's it, we're moving on. So he doesn't really work through a bunch of problems. Maybe the problems are in those exercises in the chapter, but you've seen the expanded explanation back here. I hope that makes sense to you. Also in chapter 3 are floating point numbers. Okay, floating point numbers. Let's learn it by an example, and I'll give you the names of the parts as we go. Let's take an easy float number like 20.75. Okay. So our goal is to convert that to binary. And before we do that, I have to remind you of what you learned in high school. There's something called scientific notation. Okay, and it looks like this. 3.9746 times 10 to the 3, or 1.00469 times 10 to the minus 2, or whatever. You got the idea. 8.77748 times 10 to the 6. Okay, all those are scientific notation numbers, and there's a couple of things we should observe. One is, on the left side of the point, there can only be a single digit, like the 3, the 1, and the 8. Only single digit left of point. Okay. One more thing is that single digit can't be 0. Single digit That's a digit. Is not 0. Okay. That's universal among scientific numbers in base 10. Okay, now we're going to carry scientific numbers to floating point, to binary numbers. Okay, so in base 2, we're going to have numbers that look like this, but there's only one digit on the left side. What is that one digit? We only have 2 digits to work with, 0 and 1. And the digit on the left can't be 0. So right back here. So the digit on the left has to be a 1. Digit on left must be 1. Be a 1. That's a 1 over there. Okay, I'm going to go back and use this number to illustrate how that all plays out. You ready? Let's see, no questions, I don't think. Okay, so let's take 20.75. And what I'm aiming for is binary scientific notation. Binary scientific notation. Okay, so you take the 20. What is 20? 20 is equal to 116 plus 0.8 plus 1.4 plus, that's a 1.4 plus 0.2s plus 0.1s. Okay, so 20 is 10100. Okay. Now the 0.75, I picked that to be an easy number because it's equal to 0.5 plus 0.25, which is equal to 1/2 plus 1/2 squared. Got it? Well, that's wonderful. That says that the 0.75 in binary, I didn't write the digits. There's a 1 and a 1 here. Okay. 0.75 is equal to 0.11. Okay, let's take a different number. Suppose the number is 0.375. And then you can say there's no halves here. And there's 1, like here's what, 375 is equal to 0.25 plus 0.125. Those are our fractions. This is 1/2 squared plus 1/2 cubed. This is 1/8. This is 1/4. And the 1/2 is missing. So you can see the number 0.375, it's in here, 0, 1, 1. Well, I'll show you the general algorithm coming very soon. Okay, so here, in binary then, 375 base 10 is equal to 0, 1, 1 base 2. You're all with it? Okay, let's go back to our number. That was a deviation, a detour to look at fractions. Okay, we're starting with 20.75. And we found out that 20 by itself is 10100. We see from back here where my finger is, 0.75 is 0.11. Okay, decimal on the left, binary on the right. We add them together and we get, where's my 20.75 equals 10100.11. There, how do you like that? Wasn't that a lot of fun? All right, but the problem is that's a nice binary number on the right side, but it's not scientific. See? So we have another step to go. That number on the right side is 10100.11 times 2 to the 0. And you know, from past experience, we're going to shift the point to here. That's 4 places of a shift. So it becomes 1.010011 times 2 to the 4. Now that really looks really nice. Look how scientific it is. There's that guy. We promised that the one on the left side must be a 1. And here is the part that's, well, some old books call it the mantissa. But really new books call it the significand. Same, 2 words, same thing. Okay. And this one up here, the 4. The 4 is called the true exponent. Because I don't think we'll get there today, but by next class meeting, we're going to have the fake exponent that goes with it, but not now. That's the true exponent of this number 2075. That's its real significand. And this one has a name. This one is called the hidden bit. Okay. Let's see. Shouldn't the 4 be negative? The 4. Oh, the 4 up here. Oh no, I'll tell you what, I can explain that one. Yeah. So we want to balance this out so that this expression is equal to the one right after it. You think of it this way. By moving the point, this number between my fingers became smaller. Therefore, the exponent multiplier has to become larger. So if you made the 4 negative, both this piece would be becoming smaller and this piece would be becoming smaller. That doesn't balance out. No, you're okay, Greg. No, never mind. It doesn't matter. It's an important concept. To keep equality, we can shift the point to the right, but then the exponent has to decrease. And shift to the left, the exponent has to go increase. Okay, we're not done, but that's a good intermediate step, is to arrive at this point. That's in binary scientific notation. Okay, and I usually put some of these questions on the midterm. Oh, did I explain the midterm? Okay, if you download the next assignment, next program project, on the last page, it gives you some projected dates for the midterm. And I think I wrote it up 4 days ago, but one of them is concept test last Thursday before spring break. Thursday before spring vacation. And then the programming test is the Tuesday after spring vacation. Now you should download it to make sure I don't have them reversed order, but I'm pretty sure that's how it goes after spring. So it's not fixed solid yet, but it's projected dates. Uh, you look at it and tell me if you have a time conflict or whatever kind of problem you have. And you've all been earning your privilege of open note test, open internet test, especially this one is called concepts. Okay, and there'll be problems like the one I'm solving today on the concept test. This one obviously is called program test. Okay, make sure you don't have any flights scheduled like Thursday before spring break or, yeah, just keep those 2 dates open. Okay, let's practice this once more because suppose we had, oh man, let's see if I can make 89 point, let's say a 0625. I'm picking easy numbers. And then before we're done, we'll do a hard one. Okay, suppose that's your number and the test says convert it to scientific binary number. Let's see, binary. Okay, so if you break it apart into 2 parts. 89 is equal sign 1 of 64, 25. 32, 0. 16, yes. 8, yes. 4, 0. 2, 0. And 1, 1. So we know that 89 is 1, 0, 1, 1, 0, 0, 1. Okay. Now, 0625, I did that on purpose. It actually has an easy answer. We know that 0.5 is 1/2 to the first. 0.25 equals 1/2 to the squared point. What is it? Half of that number is 0.625. Well, that's our number, isn't it? Oh, no, there's one in between. What am I doing? 125 is 1/2 to the 3, and half of that is our number, 0.0625 equals 1/2 to the 4. So except for one mistake in the middle, I kept dividing by 2, divide by 2, divide by 2, divide by 2, and over here we find out what it's equal to. So now we can say that 0.625, try again, 0.0625 equals none of these plus none of these plus one of these. And in short, it is 0.0001. That's it. Okay. This is base 2. On this side, it's 0.065625, base 10. Okay, we're going to combine that information with this information. Let's see here. Okay, so here's the combination. 8 9.0625 equals 1011001 dot. And then from over here, it is 0001. Okay, but it's not scientific. So we got to get it to scientific, which is way over here. Then it becomes 1.01100100001 times 2. This went smaller by 6 binary places. So this one becomes larger by 6 places. 2 to the 6. 6 equals true exponent. And this specific one is called hidden. And the rest of these are called significand or mantis. I'll use the names interchangeably. But that's our scientific answer. My red is just about shot, but I'll throw it out. Let's see. Okay, I've got one more to go. What happens when, see, I picked nice fractions. What if you have not a nice fraction? Okay, so someone said 101 is a radio station, FM. I don't know what they play there, but we want to convert that one to scientific binary. But let me give you an advance. The 0.3 is not pretty. That's not nice. Okay, let's do it. So 10101. We're here in the scratch paper. Okay, 101 equals 64 is the best we can go. That's 5, 6, that's a 7. And we borrow 1, leaves 37, I think. Yeah. Okay, so we write, this 101 is not binary. That's 101 decimal, 101 decimal. It's equal to 164. And then we have a 32 in here. Plus 132. We don't have any 16s. We don't have any 8s. We do have 1 4. And we subtract off the 4 and we're left with 1. So we have 0 of 2s and 1 1. Okay, so 101 decimal equals, I'm going to read this, 1100 1100 Okay. That part that's standard. The 0.3 is a mess. And we got to explain how you go at this. Okay, so we save that in reserve. We save this answer for later. So the 0.3 doesn't expand into a sum of powers of 1/2. It's mathematically impossible to get it exact. 0.3, there's no way to write it as 1/2 to the squared plus 1/2 to the 5th plus 1/2 to the 9th or whatever. It never comes out exact. So previously, this hour, we were converting integers to binary, and you use the method of divide by 2. Now we use the method of multiply by 2. Okay, we're working on the fraction part. So here it comes, 0.3 times 2. And you can repeat that. And 0.2 times 2 is 0.4. And 0.4 times 2, 0.8. And 0.8 times 2, 1.6. And 0.6 times 2, 1.2. 0.2 times 2, 0.4. 0.4 times 2, 0.8. Okay, we can keep going, but it's not necessary because it's starting to repeat a pattern. And you see, that's almost off the screen. Let's move it up. Okay, where's the pattern? The pattern is this group of multiplications repeats itself down here. That's why there's dot, dot, dot here. Okay. So that pattern will repeat itself endlessly because it's not a, it's a non, it is a repeating, I was gonna say decimal number, repeating binary number. Okay, let's put down the answer then. Is this in the screen? 0.3 is equal to, and where do we get the answers? We get the answers on the left side of the dot. This number, this number, this number, this number, this number, and repeat. Okay, those are the answers. Okay, so let's record it here. 0.3 is that first 0. 0.0. Then there's 1, 0, 0, 1. And 1, 0, 0, 1. It keeps going. Dot, dot, dot. Okay. 0.3, which is a non-repeating base 10 number, is a repeating base 2 number. It just happens that way. Okay, let's put all of our facts together. 101.3. Where did we get? Here's the 101. 1, 1, 1, 0, 0, 1, 0, 1. Now, gotta copy this thing. 0, 1, 0, 0, 1, 0, there's 2 1s. Why did I do that? 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. And I'm running out of space. But you can see, let's continue it. I have to be scientific, so I have to get this number, this point, 1, 2, 3, 4, 5, 6 places. Okay, here it comes. 1, 1, 0, 0, 1, 0, 1. Okay, that's up to the place where the old point was. Now it's going to be 0, 1. Let me just make it stand out. 0, 1, 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. Dot, dot, dot times. Okay, so the point moved 6 places. 6 comes up along. Okay, 2 to the 6. Okay, I think that's it. That is the number we started with has been converted to binary scientific notation. Okay, those bits are going to show up in registers eventually. That's another step to go. Everybody okay with it so far? So if I give you any kind of number on midterm test, the concept part of the midterm test, like 183.27, now you know what to do, right? So here's what can go wrong is sometimes the pattern that will repeat is quite lengthy. This is a four-bit pattern. What if it was a 12-bit pattern? It works mathematically, but it's just kind of a mess on your paper, on your scratch paper. I don't know if that's a good one or not. How about 88.8? The 88 on the left is easy. It's the 8 on the right that's going to create a problem. Let's do this as the last example, and then I'm going to open it up for questions about programs. Okay. Well, let's do the whole thing. 88. What is 88? 88 is 164 minus 64, 22. No 32s. 116. 116. No 8s. 0 8s. 1 4 plus 1 4. 1 2. Subtract off 2. Nothing left. Plus 0 1s. Okay, so 88 is 1 0 1 0 1 1 0. Okay, let's 0.8. Let's see how that shouldn't be extremely bad, but let's find out. 0.8 times 2, 1.6. 0.6 times 2, 1.2. 0.2 times 6 times 2, 0.4. 0.4 times 2, 0.8. 0.8 times 2, 1.6. There we started the repeat process. So this group of 4 calculations is starting to repeat itself here. This one is the same as the first one. Okay. So we have a pattern that tells us what 0.8 is. 0.8 in decimal is, we read these ones and zeros on the left side. Like that. Okay. There's the repeating pattern. It's 4 bits that repeat. Okay, let's combine it with the whole number, 88.8. 88.8 is 1010110 dot 1100 1100 1100 dot times 2 to the 0. Okay, so here we go. Last step. It's sheer accident, but it happens to be a move of 6 places again. That's okay. That equals 1.010110 1100 1100 1100 times 2 to the 6. Okay. I should put some dots in the middle there. Okay. That's it. That's our binary scientific expression for 88.8 decimal. I think, say there's more discussion about this, but I want to talk about programming for a little bit at least. This will carry on next class meeting. Don't lose your notes. And what we're leading toward is this is a big milestone, but it's in the middle of the process to establish IEEE someone 25 years ago or more had to establish what is the standard format for a floating point number in a computer. And a committee of experts, members of IEEE got together and they settled on a standard and they put it in a book as chapter 754. So the standard is often referred to as IEEE 754 standard for floating point numbers. And that's currently in use. There might be some exceptions, but that's currently in use of all the world's computers today. They use this standard for defining what a floating point number should look like. And we're getting close to it. Not quite there, but just very, very close to it. And this is the first calculation you make is to get to here. And then we're going to convert that to hex, and it'll be the 754 standard number. Okay. Standard float. Okay, can we have an example with an odd number? Yeah, sure. I have to have the starting number less than 64. If the number were 42.8, okay, then 42 is, let's work on 42. 42 is 132 minus 32, 10, plus 0 16s plus 1 8 minus 8 is 2, plus 0 4s plus 1 2 plus 0 1s. So 42 in summary is 1 0 1 0 1 0. Isn't that a weird looking pattern? Okay. All right, well. Okay, and we already know what 0.8 is. It's up here at the top of the page. So I'm going to put those two together. 42.8 is 10 10 10. And then going up here to the green ink, it's 1 1 0 0 1 1 0 0 1 1 0 0. Okay, and now it's time to shift the point. And then it's 1.01010. And then to show where the break used to be, I'll use a different color. 1 1 0 0 1 1 0 0 1 1 0 0 dot 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 times 2. And how many places do we move it? 1 2 3 4 5. It would be a 5 up here as the true exponent of this number through exp equals 5 in this example. How about 65.7? Oh, you mean odd? I thought you meant odd exponent. You mean odd number on the end of the, sure, okay. No big deal. Okay, 65. That's equal to 164, 032, 016, 08, 04, 02, and a 1. He says 0.7. Okay, we have to multiply by 2. 0.7 times 2. I think this repeats in 5 digits. Let's find out. 1.4. 0.4 times 2, 0.8. 0.8 times 2, 1.6. 0.6 times 2, 1.2. 0.2 times 2, 0.4. Can you all see that? 0.4. No, it isn't five digits. 0.4 times 2, 0.8. We're already repeating. 0.8 times 2 is 1.6. So the repetition is here. And then here starts to repeat. Okay, so we can now put together our number 65.7 equals, first this thing, 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5, 1.1, 0, 1, 1, 0. The repeating part is here. Zero, 1, 1, 0, 0, 1, 1, 0, etc. Dot, 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 dot. Okay, to clean it up, to make it scientific, it's got to move 1, 2, 3, 4, 5, 6 places. Okay. 1.02345 1. And then just for the effect of seeing where the dot used to be, this is 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, dot, 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 times 2, 6. Okay, that's it, 65.7. Goes out like that and repeats forever after. Well, let's do it next class meeting. We're going to have to cut it off at 64 bits and then convert that to hex, and then you'll see what happens. And that'll be the IEEE number. It's cool. Okay, it's all cool stuff, man. That's what we're here for. Okay, now let's go for, okay. Clock says, what is it, 3:15. We have 40 minutes left. Can anybody ask me a question about programming? What would you like to know that's been bothering you on any program? Even ones you didn't make, something you just saw posted somewhere. Think about it. Anybody have an idea? What kind of error message did you have that stumped you? Nobody had a bad error message? Usually you get a whole bunch of horrible messages that don't describe anything useful. It usually just says segment fault, your core is dumped, and then it goes away. I'm kind of confused on how to set up C++ driver portion. Can you go over that a little bit? Yes, sure. Okay. Okay, the driver, let's lay the groundwork. The driver program for this class is usually typically C++, or it could be C. They're not far removed from each other. And the purpose of the driver is give a nice welcome message about you, the programmer. Put your name in there. It says, welcome to Triangle Areas by Joe Brown, whatever, whoever. Okay. So it has a purpose, but the driver does not participate in solving anything. Does not get involved in the solution. Okay. It doesn't do any calculations. It just gives a nice purpose welcome. So what does it do? It gives a welcome message. It calls the first assembly function. It sometimes gets a return number, receives a return number, and it says goodbye. Goodbye. Okay, that's really its total role is do kind of stuff like this. So your driver program, your driver function is typically 4 or 5 lines long, and that's all. Integer main and something here, and you may use printf in C++. C++ understands printf, or you can just see out the message. That's your choice. See out. Welcome to whatever, quadratic equations. By Jeffrey Smith. And so on. So then it's going to call the assembly main function. And usually it's returning something. So let's put here double number, semicolon, and it says number equals quad, that's short for quadratic, parentheses, and then it says I received this number. Yeah, I received a number, and we'll keep it, etc. etc. Okay, and then return 0. So for us, it's just a it's a nice mechanism that lets us call all the functions in the C++ libraries, which is a larger set than the functions in the C libraries, which is nice. And that's really all that's all it's going to do. Any specifics about that is, let's point out that, oh yeah, there is something to point out. Quad is defined in another file where the assembly is, but you need to tell this one that you're going to call that function later. So up here, there would be double quad quotes like such. That's called the prototype of the function quad. And the role that it plays is that when the compiler compiles this file only, it doesn't get down here and confused and say undefined function not found. Having the prototype here says to the compiler of this main, look, this is a function that will be called later, but its body is not given here. It's going to be linked in by the linker at a later time. It lets you develop this and compile it and check it for syntax problems before the other function is even written. That's kind of a nice thing. You don't even have to have it developed yet. You can still source code check this one. Okay, that's really all. That's really all that the driver part does. So in your handouts, I usually draw you a little. This is not useful. A little diagram. If you looked at the newest posting, the diagram's getting bigger. It usually says you have a something up here written in C++, and its name is areas or something. No, its name is main, but it's in the file called area.cpp. Okay. And the line says that within it, there is a call to another function sitting in a different file. And what should we, the file could be quad. Let's say it's quadratic. .asm, and it's written in x86. Now, this diagram doesn't show the calling name. It just shows external file names. The calling name is quad. So in here is the call to quad. And inside of here, there has to be a declaration global that says quad. Near the top of the program, there's various externs, extern, printf, and so on. Extern, get, fgets. But nearby, there needs to be a global quad. Okay, and the global declaration makes the function inside of here callable by another function that's not in this file, namely here. It makes it that this one can call it into here. If the global wasn't there, it's not callable from someplace else, if that makes sense. Okay, so in all the handouts, I'll give you some kind of diagram of arrows pointing downward, meaning the one above is calling the one below it. And I hope those tell a story. Okay. Any question on the details here? Am I going in the right direction? Okay. And the global name should appear as the first word underneath segment text. .text. Don't forget the dots, they're important. The first word right after that should be the global word. In my example here, it's quad. You know, with a dot, with a colon after it. Looks like that. Okay. Anything else I can answer, anybody? Okay. If you're working on, sooner or later, the whole class gets working on different pieces. Somebody's working on assignment 1, when someone else working on 2, and someone else working on 3. That's not an issue yet. We have 4 weeks, I think, until midterm time. But if you're just getting started, you put in your extra time now. If you're caught up, that's fine. If everybody's working at this different personal pace, that's okay. Your goal is to have as much of this mastered as possible by midterm time. And then I will ask you to make a program that's practice problem oriented. That looks like something you've already worked on. And then I'm hoping you use open notes, open program, and you successfully complete the program for the midterm. So the techniques used in those, say, first 3 are the techniques you should kind of fully understand so that you can use them again. Clearly, it'd be unfair if I ask you some kind of programming technique that hasn't been covered in practical assignments and practical practice programs. I don't do that. It will be something that let's rephrase that. The program for the midterm will have pieces that you can pull out of the existing programs and reuse them. It's software reuse is a good thing. They will have pieces you can pull out of posted programs that I put on the class website, and reusing them, those are fine. You have open access to all the information, and here's the issue is you can't, how should I say it? You can read a book about how to play the piano, and you can look at all kinds of music written for piano playing, but until you actually do it, you're not a musician. You can read all the examples that I posted and look at other people's posting of assignments 1, 2, and 3, but you'll fail the midterm if you haven't actually done it yourself. You have to get your hands involved, and then you'll succeed quite well. Reading is not doing. Reading is just conceptual knowledge. It's okay and it's necessary, but it doesn't make you a programmer. Okay, can we go over the bash directing function again? Okay. Let's see. Okay, what do they call this? There's a Windows name for such a file. I'm drawing a blank on it. Bash files are in the category of script files. Bash is not the only. Okay. Okay. How do they do this? Some places, in a computer software, this circle represents the kernel of an operating system. It's the heart of the functionality of that operating system, and we programmers are not supposed to be able to directly modify it or even to read it. What we're supposed to do is access it by a surrounding program, generally called the shell. Okay, and bash is one example of a shell. That's bash is one. I think it's the most common shell of your many choices, but there's a half a dozen others that are programs that run continuously, and their job is to take your command and execute your command. So if you open up the terminal window and you input ls and a space and a hyphen and an L, this is the command, and this is a parameter to that command, and it will show you a list of files. Make a list, a nice list for you here. Okay, so that's you speaking directly to the shell, who took that command to the kernel and passed it in, and the kernel made the list and passed it back to the shell, and then the shell displays it in your terminal. That's how it works. We humans talk to the shell talks to the kernel produces an answer, and the shell brings it back to shows it to us nicely formatted. Okay, so what the bash script does is it lets you put 2 or 3 or 10 bash commands. This is an example of a bash command. You give a command to bash to do something. Okay, it lets you put a bunch of commands in a file and run them all at once. Okay, and there was something special about the first corner. What was that, Dotson? It was slash, I forgot it, /# or something. Look at the first line of every bash file. It has to be that one pair of special characters. Okay, So just like any program, it has place for comments. Pound sign is a comment. Pound sign is a comment. And then you can give it commands like this that you would ordinarily type in with your fingers. You can put it in the file. You could put right here, ls, make a space and a -L, and go on to other commands if you want. In particular, I think the question here is about compiling and linking. Those are commands that you could enter by hand, and you could compile your different files, and you could by hand put in the command and link those different files. But why do all that work repetitiously? Just put them in one bash file and let it do all the work for you. So to remove old junk, RM is for remove, and you want to remove, say, the out file, star.out. Sort of like clean up your workspace. And then you can put a command to compile the driver, G++ -M64 -C. There's a space between each one of these parameters. -SDD equals C++ 17 don't press the enter key, but keep it on one line. -O my.o, and no hyphen, but let's call it driver.cpp. Okay. So you key those into a file on one continuous line, and you can have other assembly NASM command, ASM, to assemble, that's not, don't say compile, but assemble the source file for assembly. And they have -ELF. Is it F? I'm forgetting the exact abbreviation. That's a formatting command. How do you want the output object file to be formatted? ELF is a famous format, and you can look in Wikipedia and they'll tell you more of the stuff than you ever want to know about it. But the key here is -O. We need to, what am I going to assemble? I'm going to assemble qprog.asm. So probably want something like qprog.o here. Okay. So these are a pair. You should not separate them. It says that the little o at the beginning says the output file is going to be what immediately follows me. And now you make up a name here. And it doesn't have to be .o, but it probably should be, because that's universal assumption, is that files made by compilers and assemblers are object files and they end in .o. This is how the format that .o file, and this one is the one that's being assembled. Okay, and you put that line in the bash file, and you put all the lines of your compiling. If you have 5 files in the program, then you have 5 compiling lines. Eventually, the last one is to run the program, and then your line would look like a dot and a slash, and the output file from the linker, its name goes here. Triangle dot something. In a Windows world, it would be .exe. In a Linux world, is .out, but it still means the same thing. It's just a naming convention. That's an execution statement. And then you're about ready to finish. You can say echo goodbye. And in the file, there's no special mark to mark the end of a bash file. Then you have this bash file set up, and you start it with 3 ways. 3 ways to run a bash file. You can say sh, name of bash. And this is not mandatory, but it's traditional that you put .sh as the extension. sh stands for shell. So, but it's not necessary. You could just leave it off completely and call it the name of that bash file. So this is saying, hey, shell, go run this bash file, perform all the steps inside of it one by one. You can run it by saying /name .sh, or what's the third one? I got a thing called oh, I think you write out the word bash. You can spell out bash, leave a space, and then name .sh. 3 ways to run it. You pick whatever's easy for you, but that's what you key in at this is a space marker. That's what you key in at the keyboard to compile all your files, link them all together, and actually execute it. Like up here is the execution statement, which is usually the last thing to do. Okay. You can bash, I should call that shell programming, is a big subject area, but we do this very minimal amount of shell learning just to get acquainted with it. You can actually program loops inside of your bash file and make quite complex bash files, but it's beyond the scope of what we want to learn here. This is sufficient to do everything we do in this course. In short, if you download a free ebook about shell commands. Every command that there is can be put into a bash file and executed that way. Most of the time, they are showing you how to do it one at a time. You just key it in with your fingers, and then something happens. Then you key in the next one. But every one of those commands can be put in, one of those shell commands can be put into a file, and then you execute them all in sequence without repetition with your fingers so much. Anything else I can help anybody with? We still have 10 minutes left in class. So bash is PowerShell, but for Linux. Yeah, Greg, that's it. That's it. Yeah, it's the PowerShell. Okay. Right. You can take entire courses. Usually it shows up in operating systems or something related to that. They're intimately involved with shell commands. They're trying to study the behavior of the operating system by becoming experts with all those shell commands. Okay. There are some, oh no, I can't remember. Mod probe. There are some that you can actually alter the operating system, but I would not do them because mod probe. And there's some parameters that go with it, but you can actually change functions that their behavior in the kernel. But I think of it as make sure it's on a machine that you don't care if it crashes, but don't go that deep into the subject. We're not going into here. Do you know that the strange facts? The Linux kernel has 28 million lines of source code. No. Except for 5 people in the world. All of it was built by volunteers. Around the world, volunteers submit functions those volunteers have programmed and said, would you consider this for inclusion as a kernel function that I'd like to be able to use it. And that's how the whole thing got built. To my knowledge, there are 5 people who are paid employees at the Linux Foundation who manage it, but all the work is done by volunteers all around the world who contribute ideas for it. And by, I don't know why I'm on this topic. If you'd like to download the entire source code for the kernel, it's available. You can get the whole doggone thing. It's 28 million lines of text file that's going to dump out to your computer if you'd like to just check out what they're doing. That's the open source flavor, is that it's open for anybody. And that's why those volunteers study that, and then they have an idea. Hey, let's add this new capability to the kernel. And they send it in. It's vetted. Someone checks it out, make sure it does what it is supposed to, and then it may get into the kernel. It's an odd way to build a huge system. Okay, any questions? We are at 3:45. I'm here to take another question if you got any. Nobody's questions. Okay. And hopefully you learn, I mean, I think it's true. Our author says, the author of the ebook says that you do learn about computer architecture just by making programs. You learn about the capability of XMM registers, why the low numbered ones are volatile, the high numbered ones are stable. You learn this whole architecture stuff sort of comes as a byproduct of writing assembly programs. Yeah, I was gonna. Yeah, we're learning SSE. That's the abbreviation name for the collection of XMM registers. And we're learning GPRS, general purpose registers. There's 2 others that we just don't have time to deal with. But these are key, floats and energy. Okay, class, can I help you with anything? You got bugs with your software? Let's see, this is Tuesday. Oh, if you're not going to the job fair, check in on Johnson's. He's answering a lot of questions tonight at 5:15. 5:15 Tuesdays and Thursdays. I don't have his Zoom number in front of me. He's a real friendly guy. You should ask him questions about your programming. From 5 to whatever it is, 6:30. If you can't find me, yeah, I'll be here on the second hour of each class meeting, but sometimes you have a bug on Friday night and you want quick answers. Try emailing Johnson and asking him, how do I fix this? He'll do very well to help you. Okay, are we finished? Anybody last message? Nothing. Well, everyone, have a nice evening. Keep on programming. I'm going to talk to you in 46 hours from now. Okay, you're welcome. Good evening, everybody. Goodbye. You're all welcome. You're all welcome. Goodbye, everyone. Thanks. I'll try to have a good day. Bye, Greg. Bye, Nick. Bye, Tuan. Bye, Yosef. Bye, Long. Bye, Greg. Okay.